All right, so let's get started. So we're going to start chapter 3 tonight, and chapter 3 is mainly focused on multiplication, division, and floating points. Okay, so in general we call this arithmetic for computers. So you need this chapter in order to handle your lab C, and then after lab C we're going to actually come back to some of the previous things that you've been taught on chapter 2, some of those loops and routines and so on and so forth. So tonight and next Monday we're going to focus on chapter 3, and then your lab D will be again going back on the things that we learned on chapter 2. Then we're going to have after that we're going to have the reading week, and then the midterm time and the makeup. All right. So by now we understood how the ISA actually defines several operations, right, in RISC-V. So now we're going to talk about the arithmetic for computers, like how we're going to multiply, how we're going to divide things, and how we're going to tackle floating points, which is the main focus for next Monday. All right. So here's a simple integer addition, right? So we are trying to add 7 plus 6, right? So 6 in base of 10 and 7 in base of 10. So you see in base of 2 we're going to have 0, 0, 0, 1, 1, 1. And 7 is going to be, well, actually it's the other way around. So this is 7, the other one is 6. Oh no, actually, yeah, that's correct. So the example shows we're going to add 7 plus 6, right? If you recall from some years ago when you've been doing these additions, so you start column by column. So like here you have 1 plus 0, right? So you're going to have, this is 1. Then you're going to have 1 plus 1. And then this thing on the left side is what it carries on the left next bit, right? So 1 plus 1, and then we're going to carry this 1 again on top of this. We're going to carry this 1 on top of this. And at the end, the result, which would be your 13 in base 10, becomes this in base of 2, right? So if we are doing the integer addition, which is the base of multiplication, or subtraction, which is the base of division, first of all we have to make sure we don't have any overflows, right? We don't run out of bit to show them. There are several ways in RISC-V and in general in any computer architectures that designers define how to, first of all, pinpoint an overflow, and then if we had overflow, how are we going to tackle it? Okay? So let's see here. So that was what we just saw for the addition. Let's talk about the subtraction, and then after that we're going to talk about all those different overflow situations. So let's now, instead of doing 7 plus 6, we do 7 minus 6, right? So 7 minus 6 can be represented as 7 plus minus 6, right? One way is you just do the 2th complement of 6, which was the invert of all bits, plus 1. So that 6 becomes this that you see here. So that's your 2th complement of 6. And it's actually, now we're going to follow the same procedure for addition, right? So we transform a subtraction to an addition. All right? So far so good. We have no issue here. Now, on both cases of addition and subtraction, because we are dealing with 2 values, right? So in the end, we're going to have 4 different situations. So let's see which of those are going to result in an overflow. Okay? So the first 2 cases which is for addition, A plus B. Second two cases are from. So these are add, these are sub. So far what we saw in these two examples were for signed numbers, right? We're going to talk about unsigned shortly, but let's just focus on these signed numbers. So, you see the only case that we might have an overflow, right, is that both cases, A and B, the operands are plus, right? And the result, we found that the indicator bit was minus, right? This shows that because when we add two positive integers, the result should be definitely a positive integer, right? If we found out that the resulting, you know, the resulting A plus B had a negative bit, right, as a sign, so that's a sign that, oh, something is wrong. Perhaps we have an overflow. Okay, so that's one case. The other worst case out of these four is just these two. So these two are the case of the overflow. So when you have your A minus B, right, and A is negative, B is positive, right, and the result is positive again, right? So in these cases, we can easily understand when an overflow happens. In computer, normally, so now, how about unsigned numbers, right? Mostly in RISC-V, we use unsigned numbers for memory addresses, okay? In general, and then for memory addresses, we can actually deal with overflow, because we can ignore it, right? We don't need to, unless we have a specific case for memory address. Normally we can ignore the an overflow. Also on the compiler side, before we run it on the hardware, there are so many techniques that detects overflow before we even actually run it on the hardware. Okay, so for addition and subtraction, you see that they are pretty easy to figure out when we have an overflow using the sign. All right, so the other case that you can think about it is when you're dealing with multimedia, right? So in general, we have a class of data which we call it SIMD. Perhaps you've heard about the word SIMD. SIMD stands for single instruction multiple data, right? We have MIMD, SIMD, and we have all different sorts of classification of type of data. But it just shows that you have one instruction, say addition or subtraction, but you have many data, right? You want to parallelize, perhaps. So this class of architecture of data is called SIMD. For MIMD, you have multiple instructions and multiple data. All right, but this is just for your reference. Think about an overflow, right, as a sort of a saturation. In your old, like, I'm pretty sure you haven't used those old radio knobs that you just had to turn the volume left and right and actually rotate the volume knob, right? Say when you were reaching the end point for the volume, right? Instead of just staying at that maximum, thinking about that maximum volume as all one in your bits, right? Say after you surpass that saturation point, your volume would just reset and just go to +1 out of 10, right? Become soft again. That didn't make sense in general. It should have stayed there, right? So that's another way to just find a saturation point. In many of the applications in hardware, when all bits are maximum, it stays there at the saturation point, and that's why we call it the saturation point, right? So you can understand perhaps something is wrong at this point. It doesn't reset it to just go to 0 again. It stays there. Okay? So these are other type of techniques that we can do. But the bulk of the lecture tonight is about how we're going to use addition and multiplication to implement, addition and subtraction to implement multiplication and division. All right? So let's start with the multiplication here. Okay. So going back to the high school again. So if you want to multiply this, but now it's in the base of 2. Okay, so you are trying to multiply these two values. We call the first one a multiplicand and the second one a multiplier, right? So we want to multiply these two. 1, 0, 0, 0. For simplicity, we just use 4 numbers, 4 bits actually, instead of 64 to showcase this, right? So actually, if you expand this multiplication, right? So you are, after the first iteration, when you multiply the rightmost digit of your multiplier to the multiplicand, it's going to result to this, right? You had 1, so you're going to have 1 set of copy of your multiplicand, right? So you have 1000 here, 1000. Then to carry on going on the second digit is as if you are shifting the first multiplicand to the left, right? Think about it that this is fixed now. You shift this one to the left. And now you just do this again. So now we are talking about the second row, right? This is 0, so the output would be 0. So we are multiplying this to all of that. The third row, we're shifting it again, right? That's why we are coming to the left every iteration. So this is 0 again, so we're going to output 0, all 4 here, right? The last one, which is the 4th iteration, because that was only 4, this was 1, so it's like as if I have another copy of what I have in as the multiplicand. So we're going to have 1000 here. So now we're going to have an addition at the end this way. Go down, right, down, and you just add and you get to the final product, right? So in general, you see, if we ignore the last one, assuming it was a sign bit, in general, the length of a product is the sum of the operand lengths, right? Is that clear?
No.
Okay. What's that?
The length of the product is 7, and ignoring the 7 bit is 6, and 6 is not the sum of 4 plus 4.
I'm sorry, it was plus 1. Yeah, you're right. It was m plus n. So you have m, you have n, say, it's going to be m plus n. Questions? Again? Yeah.
So what's stopping us from like just turning this to decimal and just doing that and then putting it back?
What's it stopping us from what?
From putting those two numbers to decimal and then multiplying it and putting it back.
But yeah, you understand decimal, but a computer does a computer understand decimal? Yeah. I mean, all we do, if you go back to your first chapter, we talked about all those hardware that are power efficient or they're not power efficient, all the Moore's law, all those things about your all the fabricating chips from if you recall that video that from Intel I showed you guys. So all the computer architecture that we have works only on a binary system because the signal just can go 0 and 1, right? So whatever we represent in the course or in a computer system, all of them should be at the end binary. That's why we use a compiler to, compile, assemble, compile, load, and do all those processes to start from a high-level language to a 0 and 1, a binary at the end. Because at the end of the day, that binary is just getting executed on a computer, right? Yep.
I don't understand what you were saying, like trying to explain it. Because what do you mean by ignoring sign bits? There's 7 bits there.
I'll show you another example in a slide or so. Yeah. But you got the whole idea of the multiplication, right? Cool. All right, so that was the left part. Let's talk about the right. Yeah.
Could you explain the shift? Yeah, like the process, like how did you get this?
Yeah, I'm just going to talk about it right now. Yeah. On the right side. I'm just going to talk about the right. So any questions about the left side of the slide?
Could you explain the shift and why we add it at the last? At one, so
Why do we add where? What?
this
The right side?
the left side.
Why do we add where? What?
Why we add 1 0 0 0 at the end?
Here?
Yeah.
So that's just a product of what we are. So these are the partial products, right? Because you have 4, so you're multiplying 2. So let's just go back to. So you have 12 multiply 4, right? So you have to multiply this one to the first on the right. So you're gonna have 8 here, and then you have to multiply this to the left. So you have as if you're shifting it somewhere. And then you multiply this one to this instead of this to that, right? And then you add those two, right? I mean, in general, in decimal, how do you do this? Suppose it was 14 even, right? You multiply this to this and multiply this to that, and then you multiply this to this and multiply this to that, right? It's as if you're shifting the first one left and right, right? But it's automatically done in your memory. You don't have to just report it on a paper. So here, what we do here, we start multiplying this 1 to that 4 on top. And since we are dealing with only 0 and 1, it's as if I have a copy of that, right? I have the same 1000 on the first row. So that's my first partial product because it was 1. Then I'll go here. I have 2 zeros. So on each of these iteration number 2 and 3, I'm just going to report 0 because 0 multiplied to 0. So I have 0, 0, 0, 0, 0, 0. The last one was 1. I shift again on the left side, and then that's the final product. Okay? So now let's see in the hardware in a very high level manner how we're going to implement this using different modules. Okay? So I need first of all something that controls what goes first and then what shifts and what multiplies. So that's the purpose of this control test here. You'll learn more about that later. But for now, as a very schematic high level, your multiplier has a 64-bit because we're dealing with RISC-V, right? So this second number comes here, okay, has 64-bit. Your multiplicand is going to be here, but instead of 64, we assign another 64 on its left side. You would need only 64 for this, right? Can anyone tell me why we need another 64 as an extra bit on its left?
Overflow? Also, what do you mean by shift it to the other side? Other side to what?
So shift to the left. Like in that case here, you see, these numbers are shifted to the left. At each iteration, you have one shift to the left, one shift to the left, one shift to the left, right? And then you sum them up.
Yeah.
Yeah. Do you know why do we have 128 bits instead of 64?
Because there is also being one register, but we are using 2 registers.
So why we are using 2 registers?
Because there are 2 different numbers that we are adding, so we want to like multiply. We have 2 registers, and we are like putting this.
But we already had one register for the multiplier here, right? We had one 64-bit allocated to that, which was the second number, right? Why instead of another 64 we have 128 here as for the first number? Because at the end of the day, and that's where the product is going to store, right? So my question is why we have 64-bit here, but these two are 128. Can anyone guess?
So if we multiply 264, we will need 128 to 4.
At most, you would have overflown, and you would have need only one more bit. Yeah.
You're shifting them.
Yes, because we are shifting. That's right. So is here, it starts from the rightmost 64 bits, right? And so at the start, all this 64 left side, so the most, these are 0, right? At first iteration. And this is also 0. All of this side. When we carry on, going on an iteration, this number, which was the first number, the multiplicand, right? At each iteration, is going to get shifted 1 to the left. So the first one becomes available, and we're going to use one of those, right? So 63, 62, up to the last one. The moment we reach the last one, all these first half would become empty again. So that's just an old school, lazy sort of implementing multiplication. But in this case, one multiplication of full 64-bit plus 64-bit, can you guess how many iteration I have to wait for that? For one multiplication to get completed? Can you guess? Yeah. So I'm starting from here. So that's my, suppose instead of 4 and 4, I had 64 and 64, right? So the multiplier stays here, that's 64. And then the multiplicand stays here, 64. Okay, I'm starting to just use this and add this, and then shift this to the left. Again, add the second one, shift to the left. Add this one, shift to the left. Where is it? At least, that's right. So this is a serial version. It's a serialized multiplication. You see, it's going to take a long time. I have to iterate over all of those 64 one by one and add them and find a product, right? And you see, just a simple multiplication takes a huge amount of effort to just complete it. Okay? Is that clear why? And also, is that clear why we use 128 on this ALU and the multiplicand? No. All right, so that's just a base implementation. If we serialize sequential multiplication, right, one by one, we are not parallelizing anything. We're not taking it into account any more optimization. Like that's just a pure, serialization of multiplication. Okay, so at initial it was here 0, all of the product was 0. This one came here, that was your multiplicand, and then it's going to go one by one to the left, and then you finally have your results, right? You can see more clearly in this example. Oh, first of all, we can talk about this. I mean, you already know it, but we can just go through it together. So we start the process, right? We test if the value we are multiplying, so that's the multiplier, right? Let's assume this is 1. 0, 0, 0, 1, okay? If it was 1, we go on the left, right? The multiplier 0 is the first bit of the multiplier, right? At this point, which is this 1. If it was 1, we add the multiplicand to the product. So say the multiplicand here was like 0, 1, 0, 1, right? So the first multiplier 0 is 1. So we're going to multiply it. It's as if I have a copy of this, right? So I'm going to have here add the multiplicand to the product. So I add this to the product right here. Then I carry on. I shift 1 to the left. this one we shifted one to the left, right? Also, I shift the multiplier register right 1 bit, okay? And I repeat it. If it's 0, I just don't do anything, because if it's 0, there's no need to just spend time and multiply, because the result is 0, right? You don't need to do anything, just report 0. Is that clear? Yep.
Why does the multiplier shift right?
Does anyone know? Does anyone know? Can anyone guess? If you take a look at that again here, so when we are done with the first one, right, on the second iteration, right, it's as if I don't care about this anymore, right? I got rid of it, right? I have only 100 now, right? So now when I apply this, is 0, so it's gonna be 0. Then I don't need this anymore. I got rid of it. I have only 10 now. Okay, that's why. Is that clear? So next time you use your calculator, be aware of all those computations you're causing that guy. Yeah. What is it? The control, yeah, the control manages that. The good question, yeah. Oh, we're gonna have another optimized architecture that we can get rid of all those 128s. I'll talk about it in a moment. So here's another example. So we are just trying to multiply 2, multiply 3 in base of 10, or 0, 0, 1, 0. Again, we are just talking about 4-bit numbers. We don't want to just have a 64 to make a mess. So 2 multiply 3, which is going to be 10 multiply 11, right? So let's start looking at this. First of all, we had 4 numbers, right? So with this serialized multiplication, we have 4 iteration, right? Most. Right? So first, 1 is going to be the product, the partial product actually, is a product which was the initialized product of 0 plus multiplicand, right? You see this is the product. So those that are changing in its iteration has been shown in color, in blue, right? Then I have to shift left my multiplicand, shift right my multiplier. So these are changing. I do the same again, right? Shift left, shift right. So these are changing again. Is that clear? And since if you reach something like 0, you don't waste doing any. We just don't do anything. No operation, just 0. Okay. So there has been many work to parallelize or sort of make an optimized hardware-based multiplier, right? So one of the examples is here, right? So in this case, we got rid of the 128 for our multiplicand, right? We only have 64 here, and we sort of embedded the multiplier inside the product, my product is still in 128, right? The steps can be performed in parallel, so those are steps of addition and shifting, right? So the speed up actually comes from performing the operations in parallel, okay? The multiplier and multiplicand are shifted while the multiplicand is added to the product, right? You see here, so that's the 64. 64. And the hardware just has to ensure that it tests the right bit of the multiplier and gets the pre-shift version of the multiplicand. Okay. Here actually we need one more bit at the end, because at the end, if we were just having it all one to carry out for the sign for the other. I mean, you don't have to just memorize this. This is just for your information, right? In your lab, you're just using one command as mul or different version of multiplication. But this is actually what is happening underneath that, right? Okay. There are also more faster multipliers, right? So you can use more ALUs here. I mean, you could. So now, rather than just using one single 40-bit adder, 64-bit adder, which was here, right? What if I have? So instead of using that 64-bit adder 63 times, so that single 63 times, what if I have 63 adders, like one time? Okay, I'm using more sort of hardware, but I'm speeding up the process. As if that was like 100 books here, and I'm using one worker 100 times to carry those books there and come back. It's one worker, 100 books. What if I had 100 workers? So in one time, at one shot, those 100 could just carry those books there. Okay, the amount of work is the same. My workload is the same actually. My workers are doubled, or depending on the problem, right? So there's a cost performance trade-off here. Okay. So in RISC-V, what you're going to see, or might have already seen in your lab tree, is we have 4 main category of multiplier, right? Those instructions. So we have MUL, which is doing the actual multiply, gives the lower 64 bits of the product, right? That's what we are interested in, the output of the product. We have mul-h, which is the multiply high, gives only the upper 64 bits of the product, right? Assuming they're assigned. We have multiply high unsigned, assuming it was unsigned. And then we have mul-hsu, which multiply high signed or unsigned, gives the upper 64 bits, assuming one operand is signed and the other unsigned. So these are different things that you can do with RISC-V as for multiplication. Okay. All good. So now, for now. So let's talk about division now. So you saw that the multiplication is actually addition and shifting, right? So we are basically using, and especially since we are in binary word, a multiplication can be done easily with addition and shifting. So let's see how we're going to implement the division here. The division is like much more tricky, because not only we have to reverse the addition shifting to subtraction and shifting the other way around, but we're going to have a problem here as a remainder here, right? Because of the not all the results of the division, you're going to have a perfect 0 reminder. So you're dividing this number 100, 10, 10 by that 1000, all in base of 2. We call this dividend. We call the second one divisor, and this is what we actually have as the output of the division, so quotient, right? So in this case, we have a reminder of 10 at the end. So because of this, in general, division is a much more costly operation in computer architecture in general. So let's see how we're going to implement that, okay? So look at this as if you were just dividing, I don't know, 16 to 3, right? You were just dividing it and then carry on the rest, right? So here we go to the opposite direction of multiplication. So now we are trying to divide this by this, okay? It's as if I start from the leftmost side and I'm subtracting this 1000 from the leftmost side of the dividend. So I put this here. So I have 100, 10, 10, and it's going to be 1000 here. So this will just go away, right? All I have left here is this 1, okay? And since this is done, I'll put 1 bit in my quotient here. Okay? That's why this 1 is here. Then you check, you have 110. I'm sorry, you have 1 here. So the condition is not met. If the divisor was smaller or equal than the dividend's bit, you put 1. This is the otherwise condition. That's why I need to put 0 in a quotient, right? By putting this 0, I have now 10. Is it enough? Again, no. So I'm going to put another 0 here. Now this becomes 101 here, okay? And after that, I'm going to check again. If the divisor was smaller than dividend bits, I can subtract. And finally, so here, when I'm reaching to 1010, I can subtract 1000 from it, okay? That's why I put this 1 there. So the final quotient was from the multiplication of the division of these two, like 100, 10, 10, 1000 was 1001, and a reminder is 10. Now we can't do anything about it. It just stays there as a reminder. Okay? Is that clear? The high level view? Are you still here? Yeah, you're here. So, yeah.
How does the processor know if it's signed or unsigned?
So, I mean, depending on the type of instructions, if it was a memory, right, memory addresses, they're going to treat it as unsigned. Normally, on the other cases, depending on the instruction we are using, like add I or whatever that was treating something unsigned or signed, it's going to treat it that way. But in general, normally memory addresses are unsigned, and we treat the rest, depending on the situation, again, unsigned. Yeah. Okay, so let's see the high-level diagram. So we start. We subtract the divisor register from the remainder, right? And we have two conditions. If it was smaller than 0, or greater than 0, right? We're going to test, and then we carry on shifting the quotient register to the left, setting the new rightmost to bit to 1, or you restore the original value by adding the divisor register to the reminder. Okay? Again, you have to, this is a serialization of the division, so you have to do it 64 times again, right? So just like what we had in the first version of the multiplication, in this case, now we are shifting this to the right, 128, starting from here to there. This would be still 64, and we have also the reminder also, which is initially dividend there, and the final, the rest of the space would be signed for the reminder. So you can have a look at it again as an example here. So those things that are changing again showed in blue. I'm just going to stop here. You'll have a look at it. So we start with initial values, right? The reminder is the initial reminder minus your first div, okay? You start from here at 1. This is still 0 because it was close, smaller than 0. You go left, you go right, you shift div right, and now you're dealing with that. One more. Again, this is smaller than 0, so this is still 0. Up until the point that this is not smaller than 0. That's why you put that 1 there. Okay? Again, we have another one. So you put another one. And that's going to be your final. Okay? What left at the end is going to be the reminder. So we can just use that as the final result for the reminder. Okay? Yeah. You love your calculator now? Yeah.
How much of this do we need to
How do I quantify this? How much? Like
I mean,
If we don't know it, how many marks are you gonna take off? Like, if we
you don't know how to divide two things?
I mean,
I guess you passed it in primary school.
I mean,
I'm pretty sure you can divide these two.
I mean, we can divide it, but like.
So that's fine. If you can divide, that's fine.
Do we need to explain?
Yeah, explain. Yeah, exactly. Like, is there any explanation of why this works? Why are we shifting?
I mean, this works because it's logical. It should work, right? You're shifting left and right, and then you subtract or you add.
The one in the chart. It's quite confusing.
That chart actually is sort of a design that you're gonna see more after midterm. But for now, just it's sort of a schematic view of what's been done. It's a design, right? Okay.
So on the midterm, do we have to draw that?
No, you don't have to draw it. No.
After the meter.
Yeah. Up until the midterm, you're fine.
Sorry, so the optimized version we don't need to.
No, these are just some more optimization that you need. I mean, it's good to know that there are things that can be done in optimized way, right? You're an engineer. You just start from a base, which was there like 4 years ago, and several generations later, people try to just improve it 2%, 1%, 0.5%, and that's why we arrived to this point, right? Otherwise, there was this room just doing one multiplication in the 50s, perhaps. Okay. All right. So that's the optimized divider. The speed up comes from shifting the operands and the quotient simultaneously. So now we are just shifting one to the right and the other one from to the left. Okay. And there are some more other things that needs to be taken care of. The most important issue about a division is if you want to go towards faster divisions, there is a major issue with the parallelization here. We cannot just easily parallelize hardware as what has been done for the multiplier, because the issue is in subtraction we are conditional on the sign of the remainder, right? We need to know the sign, and up until we don't know that, there's no way we can parallelize it. We have to wait for that. Okay, so now you'll understand that why in many of the scientific applications or just daily usage application, some computer architectures, compiler designers, or just coders trying to avoid certain operations to optimize certain part of the code, right? Because using each of those are costly. Say you're using it on your cell phone. Just like if you find a way to just avoid even one more division, perhaps in a large scale, you are trying to save a lot of battery in the long run, right? So these are all those small things that you can think about it from now on as a computer engineer, right? For the future. All right. Just like what we had in the multiplication, we have 4 instructions for the division. You can refer to your pre-lab C to learn more about that. And floating point, that's another story for next week. And since you are very energetic tonight, I'm just going to let you go and come back fresh at least next Monday. Okay? Have a good night, guys.